Let's look at applying the basic premise of the Runge-Kutta or Euler method for solving a first-order differential equation. So let's say we're given this simple equation, this autonomous equation, x dot plus 3x equals 0. So first, we do want to put it in state space form. That's what we're going to be putting all of our ODEs in so that we can use our numerical solvers, at least when we're in the time domain. So in this example, we actually have no forcing, which makes it easier, but I can say that my state is going to be just x, or my state vector is just x, and that will then be my x1, because x dot is the highest derivative term I have, so x1 is my only state variable, which means that I can rewrite this as x dot is, well, x dot is x1 dot. So now let's rewrite this. This will be x1 dot plus 3x equals 0. And I want to, that's going to be x1. And I want to isolate my derivative term just like I've been doing. So x1 dot equals a negative 3x1. And that means that I can identify here, it's again a very simple case. My A matrix is actually just negative 3. It's 1 by 1. And I can then explicitly put 0 for my B matrix. And I don't even have a U vector. U is really empty in this case. So my B matrix here is going to be just 0. This is a very simple case when we have an autonomous system. But really, I just want to demonstrate the principle behind this Euler method more than anything. So I'll just, again, rewrite this in a simple term. x1 dot equals negative 3x1. All right, that's the first step. We're in our state space form. Now what I'm going to do is I'm going to have my time down here, and I'll have x1, which we know is x. And I just want to do this for a couple of instances. I'm going to go into MATLAB then and do this kind of more thoroughly and in an automated way. But this way we can visualize what's happening. I'm just going to go for 1 second here. And I am going to do this for a 1/4 of a second interval. Now we're going to go in with a finer grain amount when we go into MATLAB here, because we're going to see that relatively this result we get when our time step is this large is not very good. And the sketch I'm going to make is just that. It's a sketch. I'm not going to really try to be to scale too much. I just want the general idea to go of what's happening. And remember, our x1 of 0 is 2. I'll go back up here. Our initial condition was x of 0 is 2. X is x1, so x1 of 0 is 2. So I'll say that 2 is up here and 1 is somewhere over here. Again, the blocks are not going to be perfectly to scale, and that's fine. Okay, so let's begin our Runge-Kutta method. So what we do is we have to use that initial condition first. So we know at time is 0 seconds that our value of x or x1 is 2. So I'll mark that up here. So what I'm going to do now is I have my value at time 0. So this will be my initial or my current position. I want to figure out what is my value of x1 at the next time step. Now I've already decided for this example, I'm going to go to 0.25 seconds next. In reality, that time step might be much closer. Usually the larger the time step, the less accurate our method, our predictions are going to be, or our approximation is going to be here. All right, so let's see what we do here. x1 of 0 is 2, so let's compute x1 dot of 0. And remember, this is just dx1 dt, same thing. And that's the slope of our position versus time graph. All right, so x1 dot of 0 is going to be what? Well, we can look at what we have for our definition here. Let me put a star next to it because we're going to keep referring back. That is from our state space model. So x1 dot equals negative 3x1. So for x1 dot of 0, I actually need to know what is my x1 at that time. Time does not explicitly appear in this particular example because we don't have forcing acting on it, but my x1 value does. So this will be -3 times my x1 at time 0. Well, that's 2. Right, so x1 dot of 0 is -6. So what does that tell me? That tells me the slope at time 0 is -6. So I'm going to kind of roughly put in that slope here. All right, so I know my value at time 0. I now know the slope at time 0. So what I'm going to do is extrapolate out. Again, this isn't perfectly to scale, so it's probably going to change a little bit. So I'm basically extend this line forward until it hits my next time step, which is, just for this example, the 0.25 seconds. So let's say that's roughly here. I'll calculate it out since my slope is not drawn accurately at -6, but that's the general idea. I extend that line out where it intersects my next time step. That's my value of x1 at the next time step. But how do we actually calculate that? Remember, we're using this x of k equals x of k minus 1 plus dx k minus 1 dt delta t. So it's our previous value plus the derivative at that time or at that point times delta t. So if we want to know x1 of 0.25 seconds, well, I need to take the previous point, so that's going to be x1 at 0 seconds plus x1 dot of 0 seconds times delta t, which in this case is 0.25. Now, the delta t does not have to be uniform. I'm going to pick a uniform time of 0.25 here, but it does not need to be. And in fact, when you let ODE45 run, it's going to select kind of what it deems is the best time step to use. So let's try to put all this here. All right, so that means that x1 of 0.25 is going to be 2 plus -6 times 0.25. And if I do that calculation, that comes out to be 0.5. So x1, according to this method, my value of x1 at 0.25 seconds is 0.5. So I was actually fairly far off here of this estimate, again, just in a sketch, but of what a slope of -6 looked like. So if I want to stay consistent, this is more visually what happened, is that my slope looked like this, and then I extended that out, and it brought me to 0.25. All right, so now I know, according to my method, according to my approximation, what is x1 at 0.25 seconds. Now, we're going to do the same thing over again. I need to know, for my next time step, x1 of 0.5 seconds. What is its value? That's going to be x1 at 0.25 seconds plus x1 dot at 0.25 seconds times my delta t, which once again will be 0.25, because the time step between 0.25 and 0.5 is another 0.25. So x1 of 0.5 equals, this is the time step I just had, 0.5, plus x dot of 0.25. Well, how do we calculate that? x1 dot equals -3 times x1. So I use my value of x, the previous x is 0.5, so this will be -3 times 0.5 is -1.5 times 0.25. And going through with that calculation, that comes out to 0.125. Right, so I'm at 0.5 up here, and now I go down here, put my green dot. So again, relatively, I'm down here. So my slope, I didn't mark it yet, but my slope is -1.5. I have less of a slope at 0.25 than I had at 0. So that's about what the slope calculation is, and that's how I extrapolate out to 0.5 seconds. And my value is, I'll mark it here, So this is 0.5, and this is 0.125 coming over. Okay, so let's repeat that. I want to know what's happening at 0.75 seconds. So that is my value at the previous time step, 0.5. And plus my x dot at the previous at 0.5 seconds times delta t, which again is 0.25 here. So what was my previous value? 0.125 plus x dot at 0.5 seconds. So I am going to again go back to that same definition that x1 dot is -3 times x1. So my previous x1 was 0.125, and I multiply that by -3. So my slope comes out to a negative 0.375 times 0.25. So doing my calculations here, I can get my approximate value of x1 at 0.75 seconds. And that comes out to a small number, 0.03125. And I'll mark it over here. Again, not to scale, 0.03125. And again, we have less of a slope this time at 0.5. That came out to a slope of negative 0.375. So visually, what is it doing? This was our slope, and we're extrapolating that out to our next point. All right, and finally, I'm only going to go to the 1 second mark here. So x1 of 1 second. So my previous value, and then I update it with x1 dot of 0.75 seconds times delta t, which again is 0.25. So my previous value, 0.03125, plus x1 dot at 0.75 seconds. So that's -3 times my previous x1 for this one. So that comes out to an even less steep slope, negative 0.094. I'll round off a little bit here, times 0.25. And I do this calculation, and it comes out to a small number, 0.0078. Again, I'll round, I won't put all the digits there. So 0.0078. So we are, at least on this graph, basically down here, very close to 0. So according to the ODE we were given, this numerically are the values of x1 at 0, 0.25, 0.5, 0.75, 1 second. But only calculated for that time frame. But if I kind of approximate this, this would be the curve that goes through those points, kind of to the best of my sketch ability here. So the red line is the approximate curve that it eked out here. So we're going to compare this. We'll do it in MATLAB in a moment, and I'll do it with much smaller time steps to see how accurate this is. But again, this is the premise of what it's doing is to get to the next step, I'm using my current value plus the derivative of my current value times the time step, and that gives me my next step. And I keep repeating that process over and over again until I've reached the range I wanted to. So again, by hand, we start at 0 seconds. I only wanted to go to 1 second. And for demonstration purposes, I was taking a time step of 1/4 second. So let's see how good this does. And let's compare it to more dense time steps. And for comparison purposes, let me write this down. We know what the solution should be. So x of t, I'll write it here, is 2e to the negative 3t. That's the closed form solution for this particular ordinary differential equation. So notice we didn't have to know this. We didn't use this at all to produce the numerical results. And that's kind of the point, is the numerical result, the Runge-Kutta, is not actually solving it using calculus. It's not solving it using the tricks we know from our ODE class. It is just doing this kind of update method, one step at a time, to approximate its value. And the smaller the time step, the closer it should come to the algebraic value. Now, if we had just used the algebraic value from the start, there'd be no reason to go through all these steps, because I could just put in 0.25, 0.5, 0.75, and 1, and come up with analytically the exact answer it should be. But we didn't do that. I didn't use the calculus solution at all to get this curve. So this is an example where we actually know the correct value, so we can compare all of the approximations to this correct value. So let's go into MATLAB and automate this process and see what happens as the time step shrinks. Coming into MATLAB, I'll start setting up what we have. So first in line 10, I am defining the derivative. So I'm doing this not like we would do it with ODE 4.5, but this is again just to demonstrate the simplistic version of the Runge-Kutta method. So that dx negative 3 times x, that's exactly what we were using by hand. So let's go into this nested for loop to see what's going on. This st is going to be my step size, or really it's the number of steps I'm going to use. I'm going to do this, as we can see here in line 14. I'll actually do it over 2 seconds so that we can see what this looks like for a little bit longer of a time span, but I could go as long or as short as I would want to. And I'm going to use, in this outer for loop, I'm going to increase the number of steps, which will then therefore decrease my step size. So every time I go through this outer for loop, my step size gets smaller. I'm using more steps between 0 and 2. And that's what's happening here with this lin space, is I'm using more and more points between 0 and 2 on every loop. Then I can compute my step size. I don't actually use that here, but I am computing it. Then I'm going to pre-allocate my values of big X. So big X is my solution to x of t. But again, it's only at the specific values where the timestamps, as I call them, that's what t is, my timestamps lie. So I'm going to pre-allocate it before I go into the inner loop. And then I'm going to make sure I make the first value of it 2, because that is, for this example, my initial condition. In the inner for loop, so here I am doing this for a specific time step size. In this inner for loop, I'm doing the process I was just doing by hand. So I'm going to define for my current time, k, what is big dx? That's the derivative. So I'm taking this dx as I defined it above, and I am applying my k minus first time step. This is the right-hand side of that equation I was working with before. So this is just doing negative 3 times my current value of x. Then it computes my kth value, the next value of x, using, again, exactly what we were doing by hand. What's my current value, my k minus first value of x, plus the derivative I just computed times my time step. And that gets me my x of k. I go back to the top of this for loop, I increment k by 1, and now I repeat this process. So now k is now 1 bigger. I compute my new derivative at what is now my current step, and then I compute my next value based on my current step times the updated derivative, and then this is going to keep going. So this for loop in here is what I was doing by hand previously in the small example where I was just using 5 values between 0 and 1. That's what this is doing. And then I'm going to plot as I go. And then in this outer for loop, I'm going to do the whole thing again, but with smaller time steps. So we can see what happens as the time steps get smaller, at least kind of the big picture. And then I'm going to plot them all against each other. All right, so let's see what this looks like. So if I run this, I'll explain what all the lines are as I go. I don't have a legend here because there's just a lot of lines because I keep going to more and more and more time steps as I go through. So I'll just talk about these general trends that we're seeing. So one, I guess let's look at the big picture first. This line on the top here, this dashed line, is the actual analytic solution. That is the 2 times e to the negative 3t. That's if we solved it by hand, that's exactly what we should get. That's the actual answer. Now, what happens? Let's look at this blue line down here first. So let's see what values we have. We have 0.25, x, so this is time, is 0.25. The value is 0.5. Then we go forward to 0.5 seconds, we have 0.125. We go forward again to 0.75, we're at 0.03125. We go to 1 second, we're at 0.007813, and so on. This blue line is actually what I just did by hand. Now it goes further, it goes out to 2 seconds, but we can see these values are exactly what I just got by hand. And We should expect that because it's the exact same calculation, just automated in MATLAB. But we can see, compared to all of the other solutions we have, it's not very good. It doesn't match up, certainly, with the dashed line, which is the actual answer. Now, the trend we see here is as we add more time steps, which is to say we make the step size smaller, we're getting closer and closer to that dashed line, up to a point. We're not getting, if we have a time step that's just way too small, we might be introducing other errors I won't get into now, but the general rule of thumb is the smaller the time step, the more accurate our solution becomes. So let me zoom in so we can see in a little bit more detail. We're not so backed up. So again, as we go line from left to right, we're going smaller and smaller time steps, and we're getting closer and closer to that true answer. Now, I did stop at some point. I'm using at most 256 time steps. I could get closer and closer and closer to that real answer. But there's other issues going on here that I'm not getting. I'm kind of not getting right to the dashed line. I'm getting kind of close to it. But in ODE 4.5, it's using, like I was talking about before, a more sophisticated update algorithm than we're using here. This is a very simple one. It certainly has its limitations. But as the general rule goes, these lines are getting closer and closer to the actual answer, the dashed line. So our error is generally getting smaller as we take those smaller time steps. Let me go back to the big scale. Right, so if we took a lot of divisions, we're pretty close to the true answer, because if I zoom way in here, the amount of error that we have is really not that big. So we're really zoomed in, so it looks large, but the error is at the 0.01 scale. So about the 100th of a decimal scale is our error once we have a very small time step. So again, this was just to demonstrate the very simple principle of how this Runge-Kutta or Euler method is working when we are applying ODE 4.5. Now in this case, it was just one variable, one state variable, but this idea is going to carry over as we add more state variables. We just have to take this into higher dimensions and apply just a little bit more of a sophisticated routine, but the basic premise is going to be identical when we get into higher dimensions in the next part of this example.